Thank you, Marco. Hi, everybody. It's not yet the end. Let me thank the organizer to inviting me to come here and to present these works. So we will talk within 20 minutes about vibrations and cultural heritage preservation, a new approach to protect objects. So a part of the work I will present is a part of the result of the PhD thesis of Loïc Format, held in 2023. And this work has been supervised by Nicolas Houlki-Chancelier in Satie Laboratory in CY University, Marguerite Jossic in Philharmonie de Paris, Henri Boutin in IRCAM Sorbonne University, and myself in Institut National du Patrimoine, sorry. So, vibrations are a common phenomenon in cultural heritage context. So I think you are all aware about that here. So the objects can vibrate because of works in the gallery or nearby the gallery. The object can vibrate also due to the works of the visitors, due to the climate system. More and more often, in the gallery, we have events with a very high level of music, and this music will generate vibration and make move the object, and then the transport of the object itself or the public transport very close to the gallery. So should vibration be considered as a treat? So probably some of you already know this movie. So it has been made in Manchester in 2003. So, alors non, ça marche pas, sorry. Ah voilà. So for people who don't see, you have the biggest statue, and she's moving alone, and only during the opening hours of the museum. Alors, at the beginning, the curator believed it was a joke with security colleagues, but no, it was not a joke. This is why he put the camera. And the conclusion was that the floor was too flexible and too many visitors, not too many, I'm not sure, but many visitors in the museum on the floor too flexible. So, the vibration, why vibration should be considered as a treat? So we would avoid the fall of the object. So you can understand that if there's some vibration on the floor, the support will vibrate, and under this vibration, the object can move, can be in collision with the next object, or can fall from the support. And maybe the most dangerous effect is the fatigue effect, because for a long time, after a long time, some cracks can appear on the objects. Fatigue effect in cultural heritage context has already been noticed by David Tickett a long time ago, in 2002. After works in a museum, he has noticed the apparition of new cracks on the wall paintings. More recently, in 2019, an American team has wrote a book about the influence of the public and of the work on the museum collection. So, in 2018, I have created a working group, and I would like to say that the originality of this group is to join cultural heritage institution, professionals, from museum, and also scientists, engineers from university. So in this group, we find the Musée des Arts Décoratifs de Paris, Musée du Louvre, Musée du Quai Branly Jacques Chirac, and Institut National du Patrimoine, Sorbonne Université, CY University. And the objectives of this working group is first to understand how vibrations impact objects on both a short and long-term basis, Then to propose vibration thresholds a magical number, if it's possible, but I can say no, it will not be possible, to ensure objective safety. And it will be the objective of this talk, to design anti-vibration systems appropriated for use in a cultural heritage context. So, how to design an anti-vibration system appropriated to use in a cultural heritage? No. First, we have to know the vibration we are facing. So for that, we need to do some experiment during a vibrational context. Then we have to study anti-vibrating system, existing one, and perhaps create a new one. And then, of course, make experiment and improve a system. So here, sorry, I can't see the both screen. I can't, like this, maybe. Hop. Sorry. So here you have three contexts of vibration. The first one, here, it is in the Musée du Quai Branly Jacques Chirac. The source of the vibration is the opening and closing of the door of the showcase. So this vibration can be considered as a shock, so very brief impact. And the accelerometer are glued on the support here. In the Musée de l'Homme, here, we have done measurement on the buste, la harpe des bustes. This is the name in the museum. So there are many wax bustes, and this support is vibrating under the walk of the visitor. So the duration of the vibration here is all the day during the opening hours of the museum. And then here, these measurements has been made in the Musée des Arts Décoratifs de Paris during an event. So this museum is very beautiful. There is a big hall, and in this hall, regularly, they welcome concert and défilé. I don't know the English word. So the source is, it's an occasionally source, but it's more and more frequent. And it's music with a very high level of intensity. And what we can measure? So here you have the frequency on the x-axis, and on the y-axis you have the amplitude of the acceleration measured on both accelerometers. In the green you have the noise, the acceleration measured without any vibration sources, and in blue line you have the acceleration of the vibration measured during the vibration. And what we can see within these three examples is that the main energy is contained in low frequency. We can say between 0 and 300 hertz. You can see always this energy in the low frequency. So I ask you to keep in mind this bandwidth between 0 and 300 hertz. So we wanted first to evaluate the capacity of the existing system. So the conditioning material, the foam, they are commonly used in a museum, in the storage, in the transport case, and so on. Hopla, sorry. Puff. And we have reproduced vibration excitation in a laboratory. For that, we use, hopla, sorry. Too many buttons. Three is too much, too many for me. So here we have a shaker. We can control like this the vibration. Here we have an accelerometer to measure the vibration of the source. Here a wood panel to simulate the support, the foam here, and then an object, a very nice cultural heritage object here. And we put a sensor to evaluate the ratio of vibration between the object and the source. And here we have the modelization of this system. In mechanics, it's a very simple model, one DDL system, and we have one resonant frequency and one cutoff frequency. This line, 1, is a value when the vibration on the object is the same as the vibration of the sources. So what is interesting in our objective is to be under this line. So it's to be after the cutoff frequency. Just to have in mind, this resonant frequency depends on the mass of the object and also on the stiffness of the foam. And when we measure the ratio between between the two sensors, we obtain this graph. So here, one more time, you have the frequency. Here, we are in decibel, but anyway. And the green straight line is when there is, it's a theoretical ratio, is the equivalent of 1 here. Is the ratio when there is no foam. And what we can see is whatever the foam used here, before under 100 Hertz, the displacement of the object is the same of the source. That means that the foam, the commonly conditioning material, are not efficient at all for low frequency. And worst, for certain frequency, here, the displacement of the object is higher than the displacement of the source. That means that the foam will act as a spring and will amplify the vibration of the source. So we are not happy with that. But for researchers, we are happy because we have some research to do about this subject. So but we try many materials, and we make the object change. We make the mass of the object change, and also the static load change on the foam. The static load is the ratio of the mass of the object over the surface, the contact surface of the object and the foam. And we measure on this graph, we represent the cutoff frequency according different materials. And when we can see that this cutoff frequency is not so low considering the frequency of the sources. So we are not very happy with this passive solution. This is why we wanted to develop a new solution. For that, we discuss with professionals, and we have to take into account their requirement. And these requirements are the following one. So the system has to respect the cultural ethics. It has to be reversible, non-intrusive, and so on. You know better than me all this deontology. It does not interfere with the museography. It is very important in museum, the museography. Then it has to be adapted to every kind of object, to a large diversity of objects and orders. It has to be effective when the environmental conditions change, and it has to be easy and fast to install and to remove. This is why we decide to study the active control system device to protect the holder against vibrations. Our hypothesis is to say that if the holder doesn't move, the object will not move at all. The control active has been popular around 10 years ago with a headphone. Some headphone had this system of control active, but I will explain you what is it. So we have a primary source, works, sound, transport, whatever. And we have an object. So the vibration will propagate till the object. And our idea is to add a new source of vibration, a secondary source. We will call it the secondary source of vibration. And this secondary will be in phase opposition with the original one. And the addition of these two signals has to be 0. This is called a feed-forward control strategy. For that, we need a reference sensor to evaluate the primary source, and also, is not on my graph, sorry. We need an error sensor. It's written, but we have not the drawing here. We have a sensor to evaluate the difference between the primary and secondary source. So, I will go fast on this, but we use an existing technology and we decide to transfer it according to the requirement of our colleagues from the museum. If we look at the displacement of the object, so here it is a simulation, it's not the real world. So in purple, you have the displacement of the object under the vibration of the primary source. And when the control is on, here, you have another wave which will propagate till the object, and you see that the amplitude, the vibration amplitude of the object decrease till 0. So this is a theory, this is a perfect world. So in practice, our experiment is the following one. We decide to study a wood beam. This is coming from my past. A sensor to evaluate the source. So our source is still our shaker. And the actuator here is our secondary sources. And here you will have the error sensor. What we can see, so in green, you have the signal of the error sensor without control. So our shaker is produce a white noise between 100 and 200 Hertz. So without any control, the object the vibration of the object is a green signal. When we put on our control, we have a convergence time. So you can see the decrease of the signal. And we have an attenuation of the signal measured on the object. The ratio between the original signal and the reduced signal is 12 decibel. Just to remind you that 3 decibel means that the amplitude of the signal is divided by 2. So it's a good ratio. So if we are looking in time, we have this result, but let's concentrate on the frequency response too, and we can see in blue, we have decreased the resonant frequency, the bandwidth of our system. So we are happy with this first result, and this result is a real result. It's not a simulation anymore. We will add some complexity to our signal. So now our source is changing during the time because in the reality, the signal is not always the same. So here we change the bandwidth of the signal, and we can see that our result is adaptive to the source we are emitted. Then we have improved our support. So this support has been given to us by Philharmonie de Paris. We have still our shaker. Our actuator is under the support. The error sensor, error sensor, sorry. And the result is on the same trend. So we can see that even when the object is plus lourd, the control continue to be efficient. So this result has been published in this publication. And so we are happy with the convergence time, less than 1 second. So that means that after less than 1 second, the signal, the vibration of the object is reduced with a factor around 9 decibel. And the frequency content of the signal is also reduced. We avoid, because it's a problem with the control active, sometimes we have a new frequency which appears and it's a problem. But here we manage this. I will go to the conclusion. So to continue the discussion from this morning, but I'm not sure that people were here. I'm not an entrepreneur, so I am not courageous to to create my entreprise to make this. But we are looking for entreprise to improve, not the algorithm, because since the end of the thesis, it's okay now. But now we have to improve the hardware because for the sensor, the error sensor, we are okay with the museum requirement, 7 millimeter. It's good, but our controller is a very big one, so we need to reduce this controller. And actuator, I think we can do better than this one. But for this one, we are around 3 or 4 euros for the actuator. So according to the cost requirement, we are not so bad. And the perspective of this work, so is, we are aware that this solution will not be applied on every object. So we have to continue to work on the new conditioning materials. And here is an example. What we are doing at this time is to study new material, bio-based material to do cousins with capoc, élancrin. All these things are small grains or recycling textile fiber. And when we measure the ratio between the acceleration measure on the object over the acceleration measure on the chariot, on the trucks, for example, but we can see that with the classical form, we have an amplification of the signal till 180 Hertz. So instead to be an attenuation system, it will be an amplification system. So it's not very good. And with the cousins, we reduce this amplification zone because it still exists, but it's reduced to 80 Hertz. So we win 100 Hertz. And we have also to study now the fatigue effect. For that, we have a grant for a PhD student. So we are looking for a PhD student motivated to study the fatigue effect under vibration on cultural heritage object. And just for fun, I show you a small video of the experiment because in Aubervilliers, we are happy with our place. So what is it? Voilà. Sorry, the quality of the video is not so good. So we have our small trucks, the case. Inside the case, we try different cousins. We put the sensor on the object and we measure the ratio. So thank you for your attention.
Please.
Thank you. Thank you so much for this exciting presentation. A question I have for your experiments. The frequency you were using was from 100 Hertz and higher. What about the lower frequencies? Because I think that's where even the higher damage happens.
Thanks. You're right. In this experiment, I show you only this bandwidth. It's just because of the choice of our actuator, because it's a little bit small to generate vibration under 100 Hertz. We know their actuator exists, not too big, but to emit in lower frequency. Here, it is a kind of a proof of concept. So it's not a problem for us to have a source, a secondary source who will emit under 100 Hertz. It's not difficulties, but we didn't have it for this experiment.
Thank you, Sandy. I have a question about, I don't know if it's the one previous, the slide before, the slide after. It's about your result when you actually, the signal is not constant, exactly this one. So it's all about the time response of your system. So you're saying that as you transition to these different hertz, your system is adapting and there's this sort of delay. And so here the periods are still like maybe 10 seconds. So in a real environment, does it happen that it could be even faster, those changes? And then how does that, how efficient is the system then?
What we can see here, thank you for the question. What we can see here is that the system, when the source is changing, of course, the adaptive system needs time to adapt. And we are at less than 1 second. So we have done also a kind of benchmark because there are several algorithms available to do this. And we have, it is another papers, we have a benchmark to evaluate what is important for you. Is it the conversion time or is it the ratio according to the source you need to reduce? Because if it is works, close gallery, the frequency will be relatively constant. If it is events or transport, it will be changed. So your requirement will not be exactly the same. So we have the possibility to change also the algorithm. They are implemented and we are changing according to what we want to, if we are more interested in the reduction ratio or more interested in the convergence time. But here we are less than 1 second.
Thank you for the presentation. I would have a curiosity. In these graphs, we see what kind of acceleration, and the acceleration that the actuator, let's say, is contrasting is also the vertical one, or so it works in 3 dimensions. And here we see the norm of the vector.
Yes, here we are measuring the vertical acceleration because in most of the case we have observed in the museum, it was a perpendicular acceleration to the object. Even in this case, yes. So in the last case here, we put 2 accelerometers, one perpendicular to the floor and the second one parallel, to measure the acceleration parallel to the floor. And we have noticed that the most important acceleration was perpendicular to the floor. So we concentrate only on one acceleration, the normal one.
And the actuator goes in that direction?
Yeah.
Okay. Thank you, Sandy.
Thank you.